All right, so I welcome you all once again to week 3, lecture 3, where we are going to continue with the inner product, the orthogonality, and the norm. So today's session, we will dive deep into uh, projection, vector projection, and also learn some new stuff today. All right, so as usual, uh, this is our motto, meaning that means we are talking about knowledge. Go and look for knowledge. If you don't know something, the best thing you have to do is to go and search for it. So that is why we are all here. All right, so our timeline still hold or stands from 10th October all the way to 14th December. All right, so our time, Saturdays and Sundays. So Sundays, lecture time, 7 to 9. Then Saturdays also the same thing, 7 to 9. All right. So last week we spoke about inner products. We also spoke about the inequalities, which is the Cauchy-Schwarz inequality, the triangle inequality. Then we also spoke a little about orthogonal vectors. Today we are going to talk about these three, which is orthogonal projection and the Gram-Schmidt process, and also the orthogonal subspaces and complements and norms. Okay. Now, as I said, today's session is going to more of, calculation. So I'll be very, very happy if you have a pen and a pencil, sorry, a pen or a pencil and a paper beside you to also do the calculation along. So let's recap. Last time we spoke about magnitude and direction, and we said when you have a vector, what differentiates a vector from a scalar is a vector has a magnitude and a direction. The magnitude, last time we spoke about, is also called the norm. It's also called the norm. And we said it quantifies the length or the size of the vector. It quantifies the length and the size of the vector. And in machine learning, the magnitude of a vector can sometimes indicate the intensity or the importance of the represented data point or the feature set. So you may have some features. Now, when you have a feature and you find the norm or the magnitude, for example, let's assume that you have some features. One of them, the norm is, let's say 10. The other one, the norm is, let's say 2. Now, if you compare these two things, you agree with me that the 10 is more significant than. Why? Because the norm, we said, sometimes indicate the intensity or the importance of a data point or feature set. We also spoke about direction. We said the direction of a vector tells us where it points in space, in vector space. It tells us where it points in vector space. So the direction and the magnitude, they are two independent. They don't depend on each other. The direction doesn't depend on the magnitude. They are two different things. Please, I hope you can all hear me. Emmanuel is saying that he can't hear me. Can you all hear? Please let me see if you can hear. Just give me thumbs up. Give me thumbs up so that I know those who are not can hear me, so that you know that it's their network. Okay, majority of you can hear. It means Emmanuel, please maybe log out and log in again or refresh your browser. Okay, right. So the magnitude and the direction, they are two independent things. So an example is this. Now let's look at these two vectors. We have vector 1, 1, then we also have vector 3, 3. These vectors, they will point in the same vector space. Okay, I mean the same direction. Let me use the word direction. Okay, but they will have different magnitude. They'll have different magnitude. So if you should draw our Cartesian coordinates and we label here is 1, here is 2, here is 3, here is 1, here is 2, here is 3. the vector will definitely be in this direction, which we know is going to be this. Okay. The second one will also continue in this direction, which we know it will also end up over here. All right. So these two vectors, they are pointing in the same direction, but once we calculate the magnitude or the norm, you see that they are different. That is why the direction is independent of the magnitude. When I ask you to calculate the magnitude for this, you tell me it is root 2. When I ask you to calculate the magnitude of this, you tell me it is going to be root 18. So there are two different things. Okay, they might have the same direction but different magnitude. Now, the direction is fundamental for understanding relationship between vectors such as what? Similarity. So when two vectors point in the same direction, it means they have something in common. If two vectors point in the same direction, it means they have something in common. An example is if you have a car that is heading towards Kumasi, definitely we say these cars they'll use the Nsawam road. If they use the Nsawam road and another car is also using the same Nsawam road, you say that they are all using the same route. So definitely we can say that they are going towards to Kumasi. Although it might not be true that they are all going to Kumasi. Maybe one of them will get to Nkoko or maybe in Sawam, but they are all using the same path. Okay, so definitely we can say that they are all going to Kumasi. So that is what we are also saying here is that the direction of a vector tells us a lot about these two vectors. And the process is known as what? Similarity, or the concept that we use to describe is known as what? Similarity. Okay. We also learn about unit vector. A unit vector is having a magnitude of what? Of 1. That means when you find the magnitude, it's going to be 1. And any non-zero vector can be converted into a unit vector that points in the same direction. So this is how we calculate the unit vector. We will be using this a lot in the latter part. And this process is known as normalization. So here, when you have different features, they all have different values. We can normalize all of them just to make sure that they are all of the same scale or similar scale in the interval of 0 and 1. Okay, 0 and 1. So when you do that, whatever value that you have, so if you have a vector which is 10 here, then you have 5 over here. What we can do is we can normalize it. How do we do that? We just have to convert this. We convert this and we will learn how to do the conversion. So by looking at the formula, what it's saying is that we have the vector, then we also find the magnitude of it. Then we divide it and we can scale it down so that we'll be able to get value that we can work with it. So let's look at this. So we have a vector over here and we want to apply the normalization. We want to normalize it using the formula. So we saw the formula. This is the formula here, right? So the vector divided by its magnitude or norm. So here we have a vector 3, 4. If you find the norm, it is 5. So how do you normalize it? The vector divided by its norm. So 3 over 5, 4 over 5. So this has been normalized. If you should find the magnitude, they sum up to give you what? 1. If you find the magnitude, this will give you 1. So that is normalization. So when you're doing machine learning and they ask you, or you sometimes say you want to normalize your features, this is what you're actually doing. You are bringing these values in between 0 and 1 so that your algorithms will not pay attention to higher values. As we saw previously, that the magnitude actually say a lot about the vector. The magnitude actually says a lot about a vector, where we said it indicates the intensity or how important a feature is. You understand? So if you are dealing with some features and these features they have higher values, remember your algorithm or your model is going to pay attention to them because higher magnitude means these features are of a high importance. They will be prioritized. But if you normalize it, it's easier for your algorithm to learn properly and be able to do the right thing. Okay. All right. So last week we also discussed about the vector norm, which we say we are measuring length. We spoke about the Euclidean norm, and we said the Euclidean norm is represented as this, which is the square of the individual or yeah the individual element or component of the vector. We have a vector over here. If we square it and find the square root of it, sorry, so if we square and find the square root of it, we are finding the Euclidean norm, and this is how it is represented. So the Euclidean norm can also be generalized to n dimension or to a higher dimension. So if you look at the first formula, if it's generalized to a higher dimension, it's just a matter of we squaring the individual components or elements and putting them in the square root. Okay, so this is the generalization to of the Euclidean norm. Now we saw that the Euclidean norm is or it was obtained or it is obtained from the Pythagorean triple or theorem. So if you look at the first one that we did over here, okay, if you look at the first one that we did and you compare it to this, we can say that they will move in the x direction and also move in the y direction. So if I put here to be A and I put here to be B, the length, which is the Euclidean norm, it just this will happen to form a right angle triangle. So it's just simply what the Pythagorean theorem, which this is C, which is equal to our A squared plus our B squared. My writing part will come maybe next week. They say a month, so I'm going to get it before we meet next week so that I'll be able to teach properly. All right. Then we also spoke about the Manhattan norm, which is the L1, and that one we said you just sum the absolute value of the individual component of your vector. So it's different from the Euclidean norm, which we sum there. And when you sum the square of the individual component, you also find the square root. That is for the Euclidean norm, which is the L2. But for the L1, which is the Manhattan norm, we find the sum of the absolute value of the component of these the elements of the vector. So this is a typical example for this vector, which we find absolute component of the absolute value, then also the absolute value, and we sum it. Last time we discussed that it's better to use one than the other. We realize that the Manhattan norm is good when you are dealing with outliers. It's able to work with outliers. But if you use the Euclidean norm, we saw that when you have an outlier, it tries to square it and it doesn't help our model. Depending on the project that you are working, you have to decide. All right. So this one can also be generalized to a higher dimension. Sorry, here is supposed to be n, not 2. Here is supposed to be n, not 2. So if you generalize it to a higher dimension, it's just a matter of you adding the absolute value of the individual component of the vector, and you get the L1 norm. He said the L2 norm squares value penalize such components. But the L1 norm, what it does is that it takes absolute value, treating deviation linearly. And so when you are with outliers, we prefer that you use what? L1 norm, because it treats deviations linearly. It doesn't square them and doesn't scale them up. And that is something that we don't want. Something that we don't want. All right. And for the first point here, we said the L2 norm squares value heavily. It penalizes large components. Now, when you are dealing with linear regression, which you are going to find your error, which we have the actual value minus the predicted value, or the predicted value minus the actual value, any of them can go, right? So the predicted one minus the actual value. This error is very crucial because that is what the model is using to learn. So we are saying that the L2 help us to penalize large components. So when you find the error here and the error here is large, that means a large value, that means we are going to penalize it and make the model learn the correct thing. You see it? Learn the correct thing. So in terms of error, penalizing the L2 norm is far better because your model will be learning that no, you've made a mistake. So this is not what I'm looking for. Then you penalize it, then you go back. So for the L2 norm, which is the Euclidean norm for error calculation, is far better than using the. But remember, as I said, the L1, if you're dealing with outliers, then you'll be in trouble because the L2, sorry, if you're dealing with outliers with the L2, you're going to be in trouble. Okay, but for the L1, it's able to handle deviation easily. All right. They also spoke about distance. Now, we need to distinguish between the norm and the vector distance. So if you want to find the norm, it's just a single vector. So you have the single vector and you can go ahead to find the Euclidean norm or the Manhattan norm. You have other norms as well. When you are dealing with the distance, here we are talking about two vectors. We are talking about two vectors that we are discussing or talking about. It follows them same as the Euclidean to the Manhattan norm, but just note that the vector distance, we are two vectors. So two vectors will be, and you find the norm. All right. So we have this. So we have this vector which points here 3, 1, another vector which is pointing 1, 2. So if I want to know the distance between these two vectors, it's just uh, which if you take here to be x1, then here to x2, then here, oh sorry, it's here y, not x, so here is y1. So x1, y1, then here is what? x2, y2, right? So what we are going to do is we find the square root of x1 minus x2. That is what we do. Then we add it, which is y1 minus our y2, right? So that is the same thing over here. So here you have 1 minus 3, as you can see. Then we square it. Then 2 minus 1, we square it. So that one will give us the distance between what? The two vectors. So for the Euclidean, we have a vector to a higher dimension, which is n-dimensional vector u, then another dimension v. So to find the Euclidean distance, it's just the difference between the individual component of the two vectors, then we find the square root of it. The same thing also applies to the Manhattan. Okay, so the Manhattan distance, the same thing. All right, so if a vector is here, we want to get to this place, you move in blocks. Remember, the Manhattan, we move in blocks instead of moving in a straight line. So if I want to get to this place, maybe I'll go this, go up, go this. So I'm moving blocks, okay, before I'll be able to get to my destination. So the same thing where we find the absolute value, but this time you do it between the two vectors, which is the element y. So here, if you take the first vector, the first component, you subtract with the first component of the second vector like that. So you complete everything. So it's the same thing like the Euclidean distance, right? But this time you are finding what you're you are not finding any square root. You are just finding the absolute value of the difference between these two elements. Then also spoke about the inner product. So this is where today's lecture starts from. Now, when you have a vector, which I have this vector, x1, x2, then have another. We say we can define the inner product, and this is how we define the inner product, which is we can multiply the individual components of these vectors and sum it. Look at how it is written. So the inner product is written like this. Don't get confused with the dot product. The dot product, we will say x dot y. And last time we learned that the dot product is part of the inner product. The inner product is like the broader umbrella, with the dot product is inside. Okay, so when you see something like this, or when you see this notation, remember we are defining the inner product, not the dot product. Although they all have the same definition as you can see over here, but we understand why the inner product is also defined like this. Now, this one also can be shown as this, which we'll prove later on, where you find the Euclidean norm of the vectors, which is the vectors involved, which is the vector x and the vector y, and we cross it with the angle between them. We times it with the cos of the angle between them. Now, these things we will expand it and understand what is actually happening. Now, from the formula here, we the angle the subject, which is the alpha the subject, which we have it here. When you make the alpha the subject, we have something like this. This is very, very important. We will talk about it in the slides to come, where we talk about similarity, which is very, very important. If you want to know that two vectors are similar, what they use to build recommended systems, systems that recommend items, a system that recommend movies, recommendation systems. This is what they use to build such systems, and we will do that today. We can use the inner product to determine whether two vectors are orthogonal, as this happens if and only if. So for you to be able to know that two vectors are orthogonal, their inner product gives you zero. The inner product gives you zero. Okay, Anabi, you said you can't hear me. Can you hear me now? I think maybe if you cannot hear, then it's your network. So kindly check. Okay. Okay. So when you have the inner product, last week we defined some rules that define what the inner product is. And the first one we spoke about was the linearity of the first variable. So here, last week we also agreed that we can also have another linearity of the second variable. That leads to what is known as the bilinearity, which we will use it to prove a lot of things today. So if you look at the first rule or the axiom, we take, it's like you are doing expansion. You take the x, you inner product it with a z, as you can see over here. Then you take uh you take the y, sorry, then you inner product with the z. Okay, so if you look at it, this is known as the linearity. Now that is a rule. If you look at the scalar, this is a scalar over here. The scalar came outside. Last week we learned how the scalar came outside, which we did something like uh, you have which we have a, then we also have your x over here. Okay, we did this last week, which we learned that we can put this one like this, where we have something like this, which is a x. Then you also have the x, sorry, a rather, and x like this with the square root inside. So here we said you are going to have the scalar squared, then with the inner product of the vector you are dealing with. A squared, we can find it, so that one will come out. Then you have this, which we have this over here. All right. Now, this we will learn that is equal to the Euclidean distance of the vector. So that is why the A is out. Okay, that is why the A is out. Okay. So yeah, last week we learned that. Yeah. So this is known as the linearity of the first variable, where you take the first, it's like you are expanding. This goes to this, the y also goes to that. That's what we have. Then also learn about the symmetry. That it doesn't matter, it's like commutative. Doesn't matter if you have the inner product of x and y, or the y and x is still the same thing. Then also learn about the positive or positivity, that when you find the inner product is greater than zero. And the only time zero is when the vector is what? It's a zero vector. We learned this last week. Okay, so the same proof that I did has been shown, which you have a zero vector. You want to find the inner product of a vector. So what we can do is we can still use the bilinear, where you introduce another vector, which is the same vector. That's what has been done over here. Then what we can do is we use the bilinear. So when we use the bilinear, we expect this to combine with this. Because the zero is a scalar, automatically it will come out when you multiply. So when you find the inner product, the answer you multiply by zero, you get zero in the end. Then we have a special case. The inner product of zero is zero. We learned that. Then we say that if you find the inner product of two vectors and you get zero, then we know that these two vectors are also zero. Okay. So due to the symmetry and also the linearity of the first variable, inner product can also be linear in the second variable. And that is why we said it's called bilinear. Okay. So you saw the linearity in the first variable. You can also have linearity in the second variable, where now if you look at the two, here we pick this, we combine with the y, then we pick this, we combine it with the z, as you can see over here, with the scalar coming out. So the x combines with the y, the x combines with the z. So this one is of the second variable, So because we can do it in both ways, that is why it is called bilinear or bilinearity. Bilinearity. Okay. So with the bilinearity or the bilinear law, we can use that one to find what is known as the dot product. So the dot product is as a result of the bilinearity of these vectors. So the dot product has been defined over here, that when you have an inner product between two vectors, we can use the bilinear, which this goes over here, this also goes over there, and at the end you end up getting the dot product. So you see the dot product is defined as a result of the bilinearity of these vectors. The inner product is there, but the dot product is like a bigger, the inner product is like a bigger triangle where the dot product can be found in it. Now, when you have, you saw the Euclidean norm, which you are going to use a lot. So this is when we define the Euclidean norm. This is the formula, which is for n dimension. So here it has just been stated using notation, so you don't get confused. So here you're just squaring the individual components inside the square root. Now, according to our definition of inner product, we can say that this, which we have this is equal to this, which we learned it we link these two, because that is what we are going to use to be able to prove some concepts and also do certain things. Okay, so just follow along. If you don't understand anything, what you do is that you draw my attention, or you can raise your hand. Okay, can raise your hand. All right. Okay, so we saw this one also last week, which is the Cauchy-Schwarz inequality, and this can be proven from here, which we are going to use this definition over here to prove it. We're going to use this definition to prove it. Now, if you look at this definition over here, which I tried to do this, okay, so when we come back to this place, which we have the inner product squared, then which we have this, we have the inner product, we have the inner product. According to the Cauchy-Schwarz equation, we saw that the inner product over here is less than or equal to when we have the inner product of the vectors. The same thing. Last week, this is what we saw. Last week, it was something like this. It was actually the dot product. It was something like this, which nothing has changed, which is the Euclidean norm of the vectors. This is what we learned last week. It was something like this. Now, it's the same thing that we are seeing over here, but this time we are trying to express everything using the norm. I mean, the inner product, using the inner product. So how do we, do that? So let me switch to this so that we prove this quickly. Okay. So last week, what we saw, or what you just saw right now, we have x here, then y, which is the inner product, we square it, which is equal to, sorry, I said equal to, less than or equal to, we have this, then this. Then we also have this. We saw this. Okay. Now what we can do is we saw that the Euclidean norm, if you have the Euclidean norm, we saw it is something like this. So which is this all the way to the n vector. Now we also saw that if you have an inner product, we can use the bilinear to define it so that it will end up to become a dot product, right? So we can have, or we can write this as this with our inner product inside, which it doesn't change anything. We can do this because this is 2, not n. So this is from the inner product, that if you want to find the inner product of two vectors, multiply it, so which is x to 1, y 1 plus dot dot dot, then x n y n. Okay. So it's the same thing that we have. So we can have it inside over here. So this tells you that means the inner product of a vector can also be expressed as the square of the Euclidean, because when I square both sides, this will go away, so I'll be able to get the inner product. I hope it is clear. Okay. So if it is clear, then let's go back. So what we have is this definition, which let me go to another slide, which we have x comma y, is the inner product, which is equal to this x. This is what we saw last week. Then we also have this Then we have our cos. So we are going to square both sides. If you square both sides, we end up getting this squared, right, is equal to, then we also get this one also squared, then we also end up getting this one also squared. This is cos alpha. This is cos alpha. They also end up getting this cos squared alpha. You get this, right? So now what we are going to do is, we saw when you go to this slide, we saw that when you have the inner product, we said it's equal to the Euclidean norm squared, right? We saw that. So we can replace it. So we can replace that here. We can also do the same thing for this. Then when you have square, sorry, when you cos any angle, we expect the answer to be what? Between what? -1 and what? And also 1, right? So if you cos it, we expect it to be doing this. So if it is 1 exactly, you square it, it's still 1. But if it is not 1 and you square it, anytime you try to square, let's assume if you square 0.5, what is going to happen to 0.5? Will it increase or it will decrease? If you square 0.5, will it increase or it will decrease? You can you can type your answer. If you square at 0.5, will the number increase or decrease? Oh, I didn't get any response. I hope I'm not talking to myself. All right. So Coco, or you can put it in the chat, in the public chat. Okay. So the number will decrease. So it will decrease. So because it's going to decrease, that means whatever value that we have, this equality will not hold. This equality will not hold because if you square it, it's going to decrease. So when you multiply that by this, it's going to bring this number down. That is why the Cauchy-Schwarz equation is like that. So we have proved it right now. So which is less than or equal to the inner product of, sorry, here's x. Because if you square, because the answer is 1, -1 and 1 inclusive. If you square any number between, if it is 1, it's still -1, still going to be 1. But falls between the 1 negative, when you square, it's going to decrease it. So it's going to let this part of the equality decrease. Why the Cauchy-Schwarz equation is like that. Any question? So the Cauchy-Schwarz equation has been proven. Let's proceed. So this is what I was trying to explain to you, that if you take it by definition, the Euclidean norm of a vector is the square root of the inner product of the vector itself. So if you want to find the inner product, then we will say that it is something like this, which we will use to be able to put concept right away. All right, so what about the triangle inequality? Last time we also proved that. Did you prove it? I think I did explain, but we didn't prove. So we'll go ahead and go and prove it. So the triangle inequality, we also use the bilinearity to prove that, right? So it is a build or a follow-up from the Cauchy-Schwarz equation. So let us take this to our slides and prove it right away. Okay, so let's go. Now with the triangle inequality, he said we are building upon the Cauchy-Schwarz equation. So we write, which we have our x, then y, then our x again, y. Now, which is the inner product? We expect this to be greater than or equal to 0. That means we are using the positivity axiom that is supposed to be greater than or equal to 0, right? So here, the bilinearity, which this will do this will multiply this one also will multiply that. After that, you do the same thing. So let's go, follow along. So here we have our x who inner product itself, as you can see what I do, then plus, then the lambda, which is our scalar, will come out. I've proven it already. Then the x will inner product y, right? Then plus. We are done with this. Then we come to the second one, which this will go here. Then this one also will also come here. So here we get yx, so the lambda will come out. Then we have y inner product with x. Then here the lambda will multiply the lambda, we get what? Lambda square, right? Then the y inner product itself, so we get something like this, which is greater than or equal to what? 0. Now this, because of the symmetry, we can write this the same. What we can do is we can go ahead and try to rearrange things, which we have our x, the inner product of the x here, plus we take uh, this one, which okay, so let's maintain this one like that. So here, because of the symmetry, he said if it is xy or yx, it's the same thing, right? So it's the same. So that means these two are the same. So it's going to give me 2 lambda. Then I have the inner product here. Then plus we have this squared. Then we have y, which is equal to 0. We have this. Now, if you look at it carefully, you guys will agree with me that this is a polynomial quadratic equation in lambda. Are we saying it? If you look at this quadratic equation in lambda, so here we can rewrite this. We can rewrite this as lambda squared plus 2 lambda plus 1, which is equal to 0. Oh, this is sorry. So if you pick the lambda, or you have the equation in terms of lambda, that means you will end up having a quadratic equation. And you have a quadratic equation. What do we have? This is the if you are supposed to solve this, that means the answer is supposed to be minus b plus or minus square root b squared minus 4ac, right? all divided by 2a. Now this is our equation, but let's look at something right now. Here, what we are saying over here is that this is greater than or equal to 0. This is greater than or equal to, that means we are going to have only one, at most one solution. We're going to have only one solution. Now, if I don't want to go into details, because when you have quadratic equation, I think about three different solutions that you have. Okay, you're going to have three different solutions depending on the discriminant over here. So if you pick this discriminant, which we have this minus 4ac, it determines the type of equation that you have. Whether you're going to have repeated roots, you're going to have real roots, or also complex roots. They are all here. Okay. And because because here, when you draw your graph, okay, when you draw your graph, we are supposed to intersect. We're supposed to intersect the x-axis. Okay, but when you draw it, because we are saying it's greater or equal to 0, when you draw your graph, it will just touch and it will go up. It won't cut it. You get it? So when it happens like that, you have just at most one equation. I mean one root, sorry, one root for that. So if you do substitution, which we know that by looking at this, this is your A, this is your B, this is your C. If you do substitution, you will end up getting the triangle inequality. Do the substitution right away. So this is my B. So I'll have x, y, which we square it because it has been squared. The minus. Let's neglect the 4 because it's just a scalar, and let's take this. So where is our A? This is our A, which we have, and this is our C. So because of symmetry, I don't care. I can bring the A first or the C first. So I can have it this way, which y, x, sorry, x, not y. Forgive me. Where's my eraser? All right. So which is my x here. Then we also have um, we have this. This is what we are having. Okay. But because we said this, we are just going to have at most one equation. This, when you go back or when you go and refer to your notes, you realize that this discriminant is written like this. When we are just going to have at most one equation. So why do I keep one solution? I'm sorry, not the one equation. So it can be written as this. So that means we can also write it this way. Now to carry this thing over here, we have proving the triangle inequality. Okay, sorry, let me change this. All right, so it's supposed to be x, not y. So this is what we have. Sorry, so it's supposed to be y rather. So we have this. All right, so that is that for, let me change the sign, supposed to be this. So that is that for the inequality triangle. That's sort of math over there, but it's just something simple. So that is what we got. Now, if you look at it, which if you look at it right now, okay, you realize that this one is this. This one is this, right? And we saw that we can write this as the Euclidean square, right? And that is how they have done that. That is what they've done, right? We can also do the same thing for this, which is y, right? Which is y. So that is what they've done over here. And it's the same thing over, which is y. The inner product itself can also be written like this. And that is what we have done this. Then this one is what you saw, which we have this. But this has already been defined using the Cauchy-Schwarz equation. So let's go back and let's find out how it was defined in the Cauchy-Schwarz equation. All right. So this is it. This has been defined for us. So this is what I'm talking about. It has been defined for us here. So let's go back and let's do substitution. Okay, so if you look at this, we saw this comma y, if you want to follow the Cauchy-Schwarz equation, is equal to, it's even less than, sorry, less than, which we have to have this, and y like this, right? So if we convert by looking at it, this will be replaced by using this. So this has been replaced. So the inner product of this has been replaced. So this is when we substitute using the Cauchy-Schwarz equation, we end up getting this. We end up getting this. So if you look at it, this one also can also be written as like quadratic equation. So it's like try to put it, so we can say x squared plus 2xy plus y squared. When you solve this quadratic equation, you end up getting repeated equation. So you end up getting x plus y all squared. And that is what has been written over here, right? So when you have this, comparing to this, we can, is it even at the back? Let me wait. Yes. So by comparing it, we can cancel one of the square. I mean, the squares can cancel. I shouldn't say we can cancel one of the squares. So if you look at this, x plus y squared, then this, so this square will cancel this square. And that is why we have it like this. We have it this way. Okay, so it was like this. There was a square over here, and there was a square also here, right? So the two squares. That's why we have this. So here, the triangle inequality law has also been proven here. All right. Any questions? Right. So let's proceed. The orthogonality, let's be quick. So we said when you find the inner product of two vectors and you get 0, it means they are orthogonal. When when vectors are orthogonal, it means they are not pointing in the same direction. They are pointing at two different directions, opposite direction or different direction. So you can have a vector, this vector. So we have a unit vector I here, we have a unit vector j over here. We say they are orthogonal because last time we saw these bases. These bases we saw it, which is 0, 1. If you find the inner product, which this multiply this, at the end you end up getting what? 0. So these two bases, they are orthogonal, means they point in two different directions separately. They are not on the same line. All right. So let V be any inner product space. Then if X and Y are orthogonal, they are orthogonal if and only if when we find the inner product of their sum, then it's also equal to this. Now this we can also prove it. I have to leave it for you guys to do it. So when you take the slide, you can do this. Here you can use the bilinear. You can use the bilinear. So how can you do that? When this multiply this, you end up getting this. You let me do it when you are reading the slide so that I don't get confused. Then this will also multiply this, which we have x, then y, the inner product. Then this will also deal with the x over here, which you have y, sorry, comma x, which we also have the y, we deal with the y, which is the y, this y. So when you have your this here, now this is symmetry, so I can write it as 2, right? The inner product of the y and x plus y comma y. Now we just said that two vectors are orthogonal if their inner product is equal to 0, right? So this is 0. So if these vectors are orthogonal, it means this one will go to 0. This one will go to 0. So you end up getting something like this, plus the inner product of the y with itself. So that is what we are having here. That is why you see this is equal to that. You get it? Now, this should not, scare you. This is the same thing. So this can be expressed as the inner product of itself, and this one also can also be expressed as the inner product of itself. We have seen all these things before, right? So it shouldn't be any big problem. And you are adding them, so that one too can also be expressed as this. All right. The next thing we want to talk about is the geometric interpretation of inner product. Now this is what we need to be able to understand why inner product is very, very important. So you have a vector x heading in this direction. Now there's another vector y in this direction. So this vector and this vector. We want to find a way to project x onto y. Those of you who did engineering, we call it vector resolution. Vector resolution. I want to resolve the x into the y. So you remember engineering, you have your Cartesian coordinates where here is your j, here is your I, and you have a vector over here and you have to resolve it. So you have to resolve this to this, you also have to resolve that into that. So this resolution tells you the amount that specific vector is in that. So if I want to resolve this x in here, I just want to know how much or what is, how much of x is in the y. That is what I want to talk about. That is where the similarity comes from. That is where the similarity comes from. How much of this x is in the y? Is it perfectly aligned? Is it so when you do that projection, you're able to know that whether two vectors are of similar or they are different. So let's look at the diagram carefully. So I have my y here, I have my vector x. I want to project the x onto the y. So what can I do? I have two options. Look at where the x ends. Where the x can draw a perpendicular line all the way to hit my y, which is perpendicular. So this one tells you that, so the xp, which is this xp over here, tells you the amount of x in the y, the amount of x that is in the y, the amount of x that is in the y. Now, if here is my xp and here is my x naught or x0, from vector addition, we will see that moving from here to this place is the same as moving this root. So your x is equal to the x naught plus the xp, which it makes sense. Now, if we come back, we will see that if you make x naught the subject, then it's going to be the reverse. So x naught will end up getting x minus xp, right? And that is what we have here. So x naught has been made a subject. That is what we are seeing over here. So if x naught has been made a subject, what can we also do? Now, let's look at what we can do to our xp. So let's go look, pay attention to the diagram again. Now, if you look at your xp, which comes here, sp is also in the same direction as y. So I can say that sp is y multiplied by some scalar, and that scalar will definitely shrink. Sorry, xp rather, not x. Let me clean it and correct it. Okay. All right. So it's supposed to be xp rather is equal to some scalar multiplied by. So you will tell me that the scalar that's going to multiply y is going to be less than 1, but not negative, right? Because it's going to shrink it. So that's what we have over here. Now, if you check, that is what we have. Now, since x naught is orthogonal to y, x naught is orthogonal to y because it's perpendicular, as you can see over here. So if x naught is orthogonal to y, then it's telling you that if I find x naught, the inner product of x naught and y, I'm supposed to get 0. So if I come here and I say, okay, the inner product of x naught and y to give me 0. So all I have to do is just do substitution. So x naught, I just do substitution, replace it with this, and my y also. Which my y, which we said is y, let me verify a minute. Okay, so it's the same thing. So it's the y, we are using the y, not the xp. I thought it was the xp. So that is what we are doing here. So the xp rather will change. So we get x naught is equal to your x minus your cy because we have changed, we have done substitution over here. So that is what we have done. Now when we go on and do the calculation, right, we will end up getting this, which x naught is equal to x minus the inner product of x and y and the inner product of y multiplied by the y itself. So this is the projection. So we projecting x onto y. This is how it is expressed. So if you look at it, look at the diagram carefully, we are projecting x onto y, and this is the projection. So the formula tells you that the projection of x onto y is expressed. So we can write it formally by using this formula, which tells you that the projection of x onto y is the inner product of the two vectors divided by the inner product of the line you are doing the projection onto multiplied by the vector of the projection, the one that you are doing projection onto. Now, if you look at this, we can also, get something over here, which we know here, these two lines are parallel, right? This is parallel to this, okay? So any angle over here will alternate with this, right? So if here is equal to pi, which is 180, then if here is some angle, okay, sorry, here, not the whole angle. If here is alpha, then here becomes alpha, then here is what? Alpha this. Now this is the angle. So here is my x, yeah, here's my x, here's my y. Now remember the cosine rule. Remember the cosine rule, right? Yes. So the cosine rule, which we used it in physics before, this is the cosine rule. If you look at the diagram carefully, here, what are we doing? The magnitude of this, multiplied by the magnitude of what? X over here, then 2 times x and y cos the angle over here. And that is what has been shown over here. So if you look at this, that is what has been shown over here, which using this, the cos of this multiplied, sorry, this added to this minus, when we multiply them, cos that. Now when we pick this, which we have done over here, when we pick this is very, very crucial to us. It is very, very, very important, because that is what we can express, able to know the cosine similarity. So if you want to know the cosine similarity, meaning you want to know if two vectors are similar or they are pointing in the same direction, we use this. And if you go on to find the angle, you can find the angle. But what is important to us is just calculating it. So we have an example which these two is the same projection. Let me skip this. All right, this which I've explained everything. So the cosine similarity, okay, the same thing over here, but this time written in inner product form. Right. So let's take an example, practical example. I want all of you to take your pen and pencil. Let's work this quickly so that we can allow it a few minutes. So we have okay, someone, a lady called Jessica Martins. Jessica Martins, you watch a movie, and the movie that you watch, please write this one down. Corrected these features. 3. And Jessica went on the platform again, and when he went there, they've recommended two, movies, or they recommended 2 movies. Now, because Jessica has its own interest, for example, when it's Netflix, they recommend certain movies. Now, that which movie should we recommend for Jessica? Should we recommend this movie with this feature, or this movie with this feature? And that is what you get. So drawn in our Cartesian coordinates, we have 3 different vectors, which is movies with their features. And we want to know that should we recommend the B or the C to Jessica? We can do that using the cosine similarity. So I want you guys to put this formula down, and let's calculate it, do the calculation right now. All right, so this is it, which is cos xy is the inner product, or if this is not clear, we can use this one, which we can also use this. So you can put this one down, you can use this one to do the calculation. You can use this. Okay, so put this thing down and tell me which of the 2 movies would they recommend for Jessica to watch. All right, so I'm giving you guys few minutes. Okay. So which of the 2 movies? So this is the movie Jessica watched. You watch the movie A, which is 1-3. Now, after watching this movie, they want to know, or Netflix want to know, they want to recommend, not that they want to know, they want to recommend movies for Jessica. They are not sure, but they went to find out the movie Jessica watched, and this is the movie Jessica watched. So based on this, the movie Jessica watched, they will now be able to recommend. So can you go ahead and do the calculation quickly using the formula, which we said cos alpha is equal to A H T. I think I made a mistake with the formula, right? Let me explain it. Okay, so I hope you are working. Okay, so let me show you the formula again. All right, so this is the formula. If you want this, this is fine. Yeah, this is fine. So the inner product divided by the ingredient norm. So let's be quick, guys, please. So maybe 3 minutes is fine. Do out and calculate it for me. ASAP. If you finish, you can type your answer. Who is done? Okay. So you can do the calculation. I don't want to waste time. So if you find it, you see that when you find the causal similarity between the A and the B and also the A and the C, this is what you get. You will get this, you also get that. Okay. Now, if you look at it, you will see that the movie Jessica watch and the C, look at the value they are getting, and look at the movie Jessica watch and the D. So definitely Netflix will recommend the C movie. We definitely will recommend the C movie because if you look at it, this value is higher one than this. So here we said they are almost aligning. These two vectors are aligning. So that means they will share certain characteristics or they will share certain features or they have certain things in common. Right. So a higher cosine value signifies a greater similarity. So therefore, the movie represented by vector C with a cosine, this will be recommended to Jessica. So I've explained it. All right, so we also spoke about orthogonal and orthonormal bases, which we said through the lens of similarity, orthogonality means that one vector does not contain information about two vectors. So when two vectors are orthogonal, they point in what? Different directions. They are not pointing in the same direction. So we can define that. So if you have a V, which is a vector space, and we have a basis over here, we say if the bases are orthogonal, it's the same thing, the inner product will give you 0. So one thing you guys know, if I have this, you all know this basis. Sorry, this is 0. This basis, we've seen it before. We also have 0, 1. You agree with me that when I find the inner product, this time this is what? 0. This time this is 0. So the inner product of I, J is equal to 0. That tells you that they are orthogonal. They will point in what? Different direction. Different direction. Different direction. Are you okay? All right. So I want you guys to tell me whether this base is orthogonal. Just 1 minute. This base, is it orthogonal? Is this base orthogonal? Just look at it and tell me. You can type it. Is this base orthogonal? All right. Or you can send it in the chat. Or you guys cannot type in the chat. Okay, then let me create a poll right now. Um, so is the base orthogonal? So just tell me. Daniel said no. Okay, that is correct. Who else? Is it only Daniel? Okay, so more people are saying, 3 people say no. Is it true? I want more answers. All right, so 4 people, no. 6 people saying no. All right. All right, so it's not orthogonal because when you multiply it, okay, when you find the inner product, sorry, when you find the inner product, you not get 0. It's not orthogonal. All right, that is good. All right, so when we said S is orthonormal, we saw this last time that apart from it being orthogonal, I need to have a unit vector. Sorry, a unit norm, not a unit vector, a unit norm. A unit norm. Right. So when you have your vector here, what when you find the inner product, that means when you find the inner product and the vector I is equal, no, vi is equal to vj, as we are saying over here, okay, you get 1. If they are different, you are going to get 0. So let me explain it. So here there are 2 things that is happening over here. One is the unit norm, the other one is orthogonal. One is the unit norm, the other one is what? Orthogonal. So let's have a norm, a base rather, which is 1, 0. We have this. Now, if I find the inner product of this, of itself, what I'll get what? Sorry, here is 0. We expect me 1, right? I'll get 1. So that is why we have the 1 over here. When I is equal to I, you get 1. But if I is not equal to I, that means if I, here is I, sorry, if I is not equal to j, so here is 1, 0, then here is 0, 1. If they are orthogonal, that means they should give us 0. So this will give you 0 plus 0, you get what? 0. You get it. Then also speak about a unit norm. So if I find the unit norm, which 1 squared plus 0 squared is still 1. 0 squared plus 1 squared will still give you 1. So that is that. All right. So one of the things that we use a lot, last week I spoke about it, is the orthonormal basis. When we deal with the linear combination where you have a vector, you can have a vector x, and you express the vector as this is c1, v1 plus dot dot dot, then cn, then vn. Okay. So these are scalars and these are vectors. I'm expressing this vector as a linear combination. We did this. When I told you that one of the issues that we face is we getting these scalars. Getting the scalars is very, very difficult because you use the basis, all right. So if you use the basis, all right, but you getting this, and the scalar is what is difficult. So that's the question over here, saying that how do we find the coefficient? How do we find the coefficient? So what we can do is we can use the autonomous, and autonomous makes the situation simpler to solve, and that is what we are going to do. So let's have a vector V of vector space and S of autonomous basis, and all these things are all in the vector space V. We can express that vector using the autonomous basis in this format. Now, this is not clear, but let's come here so that it will make a little bit sense to you. So I have this vector here, and I want to find its, this is the linear combination of this vector. Now, for us to be able to determine the scalars, that is where we said that one is where the problem lies, right? But we can use the autonomous basis to help us. And how do you do that? And that is what we are doing over here. You find the product of the vector and the autonomous basis, then it will be able to get you the coefficient, which is the scalar. Once you get the scalar, we know that the autonomous basis is the vector divided by its Euclidean norm, and we just do substitution. So once we're able to get this, which will solve an example for you guys to see, we just substitute this and we are good to go to be able to get whatever we are looking for. Okay, so this is an example. Let's try to do this right now. So follow along. I'll be quick. We don't have time. So here we have a vector here. They say we should find a linear combination of this vector. You've done this thing already, which we did it. I think we had 2.5 and 0.5. I remember. So we are going to learn how to use this autonomous basis to help us do the calculation quickly. So how do we start? First, we can rewrite 3. Let me get to a new place so that I can do that quickly. So it's 1, 1, then 1 negative 8. So let me switch quickly and let's do it right now, then we can proceed. All right, so we have the basis. So the first base we have is 1, 1, right? Then we also have this base, 1, negative 1. Is the bases here, are they orthogonal or not? Are they orthogonal? Go ahead and tell me if you think these bases are orthogonal. Okay, I think you guys cannot. All right, so is the base orthogonal? All right, so I want to on right now. Okay, so all of your chat is locked, eh? Wow. Oh. Sorry, I want to unlock all of you. So let me do that right now so that you can go quickly. So you can type now in the chat. Okay, so you can now type in the chat now. All right, so yes, it's orthogonal. Yes, so it's orthogonal. Yes, by looking at it, you see that when you find the inner product, you get what? 0. All right, so let's try to express it. Now, if you are expressing this one as linear combination, you will get C1, then you have what? 1, 1 like this, right? Then C2, then we have what? 1, negative 1. This is what we get. Now, here you end up getting system of linear equation where we get what? 3 is equal to C1 plus C2. Then we also have 2 is equal to C1 minus, sorry, so minus uh, C2, right? Now this, you can solve it right now for me, right? Using linear simultaneous equation, which you can get the answer. But what about if you don't get something like this, you get something complex? What can we do? That is where we said we can use the autonomous approach to do that. So by defining it, we can say that uh, we can say that 3 2 rather, was it 3 2 or 3 2 3? Let me confirm it properly. Okay, it was 3 2 rather. Okay, not 2 3, 3 2. All right, so to solve this, the first thing we have to do is to find the ingredient for this. So we can make this one U1. So U1, if you want to find the Euclidean norm of U1, I want someone to tell me the answer. Then the Euclidean norm for U2, you can type it there. Let's be quick. The Euclidean norm for U2, the Euclidean norm for U1. Let's be quick. So this is U1, this is U2. What's the Euclidean norm? This is what? Okay, that's root 2, correct? Then what about the U2? The U2. Okay, that one is root 2. Okay, that's correct. Please, let's all participate. Okay, now we can use the autonomous basis to help us get the C1 and the C2 quickly. Okay, so what we can do, if you have any vector given to us, so we can express it as the product of that vector and the norm. Then you also have the norm over here. Sorry, I think I'm getting tired. Not the norm, but the uh, autonomous base. The autonomous base. So the vector, the inner product of the vector and the autonomous base multiplied by the autonomous base. So what you can do here is we find the inner product. The vector is this. So here we will have 3 2, right? And the u that we have over here, if you want to find the autonomous base, is going to give us, which we know it to be this, which is equal to the vector divided by the magnitude. Okay. So if you do that, you end up getting which is 1 divided by root 2. That is what, so we are doing it. So here you will get 1 divided by root 2, right? Then we also do that for the other one, which is 1 divided by root 2. Sorry, forgive us. Our writing part will come very soon. So this is for the U1. Then plus we do for the U2, which is also the same thing. 3, 2, then we have, if you look at it, that one is 1, so it's going to be 1 divided by root 2. Here is negative 1. Negative 1 divided by root 2. You have this. All right. So when you multiply by looking at this formula, we find the inner product. Then each one you multiply by the autonomous base again, which is our U1. So here, if you multiply, you end up getting this. Then you multiply this. So you end up getting, if you should do the calculation well, you end up getting 5 divided by 2 root 2, which is U1 plus. Now I want you guys to do this thing for me. So multiply this by this, multiply this by this, and tell me the answer. Okay, this is U2. So 3 multiply 1. So we find the inner product of this. Let's be quick. Who is done? Who is done? Okay, I can see. Okay, so you end up getting 2 root 2. All right, so you get 2 root 2. 2 root 2. Okay, so 2 root 2 rather. Now, so now that we've gotten these values, we are done. So the next thing is for us to do substitution so that we can get, you remember I said the U is equal to the vector divided by its magnitude, right? So what we do is that we carry the whole of this. Come and put it over there. So we have 5 divided by 2 root 2. And what is the vector? The vector is what? 3, 2, right? So if we find this, okay, if you find this, if I want to find the magnitude for this, what do you think the magnitude will be? What do you think the magnitude for this will be? Root 13. No. I think we are supposed to use this. Sorry, we are not supposed to use this one, rather. Not this. We are not supposed to use this. This will give us error. Okay, so we are supposed to use this rather. Okay, so we use the basis because here is even basis, not even the vector. So we are supposed to use the basis. So here you told me the 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 magnitude is root 2 here. Here is root 2. So we do substitution over here. So it's going to give you the v divided by root 2, then plus root 2 divided by 2 multiplied by v divided by root 2. So this will cancel this. So we end up getting 5 divided by 2, comma This also cancel this, we get 1 over 2. If you remember last time we had what? 2.5, then also what? 0.5. So this is how you can use the autonomous basis to do that. All right. All right, so the last one, and we are done, is the Gram-Schmidt process or Schmidt. I don't know how to pronounce it, but you say Schmidt, some say Schmidt. I don't know how. Any of you can correct me. All right, so this one is used to be able to get the autonomous basis. Okay. It's an algorithm which I will inform the TAs to, let you guys, build it. Okay. So how do you build that? Let's go straight or let's jump straight away to it. So I don't waste time. All right. Okay. So it is built on the vector projection. When you want to project a vector onto another vector space, right? So let's assume you have autonomous basis over here, right? And if you remember, if you saw what we did where you try to have a vector and you're expressing it as a linear combination, and we said you can use the autonomous basis to be able to get your what? Your coefficient, which is your constant. Now, the question comes here, or the question that we normally ask is that these autonomous bases that you are using, one, are they independent? How will you know? Because if the bases are independent, you remember, if the bases are dependent, if the bases are dependent, you remember what will happen. If they are dependent, the span, we won't be able to get the span, and the vector, you can express one vector in terms of the other, and that is what we don't want. So we want to be able to have a large span. If it is spanning the whole Cartesian coordinate, we want it to span the whole Cartesian coordinate. It shouldn't span a point, it shouldn't span only a line. So we use this process to help us to be able to, get that. And we are going to go through it right now. So first, we will take a set autonomous basis, and the first thing we'll do is we will find the autonomous base. So please make your pencil ready. We are going to work along and build this together so that by the time we finish, you guys, I'll not have any problem again. All right, so let's write this thing down. All of you put this one down. All of you, write it down quickly. We are going to use this one to understand the process. Okay, I don't want to explain, then we'll come back and come and do it. So write it down. I'm writing my own down. So all of you, I'm giving you, write it down because you're all going to calculate. I want you to understand it so that when we are coding, you can write your own Python script to do this. And you can save it as a library too as well, or you can even have it as your machine learning module that you build. All right. Are we clear? Okay. So now that you've written this thing down, let's go. The first thing we will do is you're going to define. So we are all going to work alongside with me. So please make sure we are all doing it together. Okay. I've opened my book. You also open your book so that we work together. The first thing we will do is you are going to define this. You're going to define this. So you saw the vectors. The vectors you saw, you are going to define that. So E1, you just write E1, which is equal to, or we are defining E1 as V1. Now what I want you guys to do is to find the autonomous base for the V1. With the V1, we saw the V1 as 1, 2, -2, right? Now, if I want you to find the autonomous base for me, I believe you can do that. So go ahead and find the autonomous base for me. Go ahead and find the autonomous base for me. How do you find the autonomous base? We learned it. So because it's V1, I can say U1 is equal to the vector, right, divided by its magnitude. This is V1 divided by this. So when you finish, you can write your answer. I know it's going to be a little bit complex, but check. I don't know whether the notes, can you even type inside the notes? I think the notes we can't type it. Yeah. But you can try and type it in the chat. Let's see. Please, let's all do it, please. Let's all do it. I'm even doing it myself. All right. I'm just praying we get our writing part this week so that all these things I can prove it quickly and we proceed. Okay. All right. So it's almost 9. All right. So if you do this, those of you who did it, you get the U1. You end up getting, who is that? End up getting 1 over what? Root 3, right? Then 2 over what? Root 3, right? Then minus 2 over what? Root 3, right? Did you get the same thing? So you end up getting 1 over root 3, 2 over root 3, and minus 2 over root 3. So that is that for our E1. So we know our E1 now. So the magnitude for E1, if you want to find the Euclidean norm for E1, that is going to be root 3. Is it 3? No, that is 3, it's not root 3. You get 3 rather. It's 3, not root 3. I think I made a mistake because you get here to be 9, right? So it's supposed to be 3. So it's going to be 1 over 3, not root 3. Then 2 over 3, right? Then a minus 2 over 3, right? You get this. So the magnitude is 3, for the Euclidean norm is 3. So that is for the E1. Now to find the E2, we know that the E2 and the E1 should be orthogonal. Okay, so that means we can find their inner product. So let's move. So if you find the projection, this is what we are going to get. So what I want you guys to do is, you know the V2. You say the V2 is equal to 3, 6 minus 6. So 3, 6 minus 6, right? Then minus. Then you find the inner product of the V2 and the V1. Sorry, the V2 and the E1, sorry. The E1, we've calculated it, which we had 1 over 3. We had 1 over 3. So we get 3, 6 minus 6. The inner product is 1 over 3, 2 over 3, the minus 2 over 3, right? Then all divided by, you find the inner product. Oh, here is supposed to be 1. Here is supposed to be 1. I'm coming, guys. I think I made a mistake doing that. Yeah, it's supposed to be 1, not 2. It's 1, please. It's not 2. So that place is 1. Okay. So you find the inner product of itself, which is also going to give 1 over 3, 1 over 3, so 2 over 3, then 2 over 3. Then you multiply by itself. Okay. So when you do that, you, for this, for the second one, you end up that you are going to get E2 to be 0. If you do it, you're going to get E2 to be 0. Once you get E2 to be 0, it's telling you that means the E1, okay, is just a multiplication of the E2. The multiplication of the E2. That means the E1 and the E2, they are dependent. That is why you are getting 0. So anytime you are using this Gram-Schmidt process and you get any of the calculation to be 0, telling you that the previous orthonormal and the current one that you are working, they are dependent. That is why you got 0. Okay. So if you do it for the E3, You also go on and you get the magnitude to be root 10. Then you can express it. Okay, time is one. So uh so this things explain, okay, it just explain all the things that I wanted to, us to do, but because we don't have, I don't have my writing pattern, that is why we are just delaying like that. Okay, so when you follow or when you go through the slides again, you'll be able to prove these concepts yourself. All right, and as I showed you so this one is talking about the linear independent, but if they are linear dependent, okay, it gives you zero, it produces zero at the end. It produces zero at the end. All right. Okay. So this is the question. Try it off. If you have any challenge, you can DM me. Okay. We will discuss it or I will explain everything to you. All right. So any question? Any question?